Good morning. Welcome to Krishna's class. Let us continue with the open mapping theorem. In fact, more or less a consequence of the open mapping theorem, which is given in the form of a corollary or what you call a theorem. I have stated the theorem here. Says both x and y are as before Banach spaces, and T is a bounded linear transformation of x onto y. It's 1 to 1 and all. That means we are assuming that T is both 1 to 1 and all. In addition to that, see, in the previous theorem we have assumed that T is 1 to 1. T is onto, but now we are additionally assuming that T is 1 to 1. And then look at the consequence of that. Then what we can say is that, because since it is 1 to 1 and onto, there is an inverse mapping that exists, and the inverse mapping is a linear transformation from y to x, which is also onto. Okay, so that what happens is that we can show that T inverse exists, and T inverse is a bounded linear transformation. This is the conclusion that you have. That is, in short, we say that is, if T is a bijection, then T inverse exists, and is bounded by that's it. Now the bound can be actually calculated from the bound of T. That is, the reciprocal of the bound of T is what you have. It's the norm of T inverse is less than or equal to delta inverse, where delta that appears in our theorem in the earlier discussion. Okay. So this is a linear transformation from y to x, which is also 1 to 1 and onto, and is of course bounded. That is the conclusion. Now, what is the consequence of this? Now, we said that T is an open map. That means it maps open sets from X onto open sets. Now, look at T inverse. In this case, T inverse exists, because in the previous theorem we had not assumed that it is a 1 to 1 map. Therefore, we could not have talked about T inverse. Now, since we are assuming, in addition to T being onto, it is also 1 to 1. That means T is a bijection. It follows that T inverse is a linear map from y to x. That is the main conclusion of the theorem. And what happens is that T inverse has the property, you see, already T is a continuous map, T inverse is also a continuous map. And now, if you work on T inverse, what happens is T inverse is also an open map. Therefore, both T and T inverse are open maps. T is an open map from x to x onto y, whereas T inverse is an open map from y onto x. This is the conclusion. So, in such a case, both T and T inverse are open maps. They are already continuous. T is continuous, of course, and T inverse exists, and T inverse is a linear transformation. It's a bounded linear transformation from Y to X, therefore it's a continuous map. And that implies T is open as well as T inverse is open. Okay, so both T and T inverse are now open maps. So this is the extra information that one can prove if we further assume that T is also a one-to-one map, or when T is a bijection, this is what happens. Both T and T inverse are bounded linear maps. That means they are continuous, as well as both T and T inverse are open maps. So let us prove this theorem. Now, the purpose of this talk is just to complete this process. It's a very short lecture. So we will just prove this theorem and then leave it there. So that concludes our discussion on the open mapping theorem. Suppose, see, from the given conditions, of the theorem, we have a delta positive such that Tu contains delta. Now this, both U and V are where U contained in X, V contained in Y are unit open unit balls in the respective Banach spaces. So U is the unit open ball in X and V is the unit open ball in Y. And what we have proved is that there exists a delta positive such that Tu contains delta U. Let's look at the geometry of this, then it will be easy to understand what is it. Okay. Okay, so what we have is the following. So pictorially, this is what we have proved. I mean, even if we do not assume T is one-to-one, still we have this result. So this is, suppose this is X, suppose this is Y, this is just a schematic diagram, and then this is the unit ball in X, which you call U, and T maps this into This is TU. Okay. Now what it says is that there is a delta positive. Suppose this is V. Then there is a delta positive such that this is the delta V. Delta V is essentially the ball with center at the origin with radius delta. And V is the ball with center at the origin in the y space with radius 1. Okay. So this is the picture that you get. This is your T. This is U is a unit ball. So this is the radius. Okay, what does this mean? Let us look at the implication of this. This is what you have. So TU contains delta V, as I have marked. So TU delta V is a subset of TU. Okay, so this is what we proved last time. Okay, what is the consequence of that? Now you see that if norm of x is greater than 1, then we have norm of Tx greater than delta. So this is the conclusion that you have. See, if norm x is greater than 1, that means if you are somewhere outside this disk here, its image is not going to be anywhere here, but it's going to be outside TU. Actually, therefore, what happens is norm of Tx, suppose you take an x here, this gets mapped to some Tx. Now you can see that distance, the length of Tx is greater than. In fact, this is true for every x with greater than 1. And of course, even greater than or equal to 1, this is the case. Okay. Therefore, what we do, we take now the following. We take x and look at x divided by norm x. Of course, we take x not equal to 0, so that this makes sense, and this, the norm of this is equal to 1. Therefore, what you can conclude, you apply this result. Therefore, this implies norm of because this is equal to 1, you see that because if you apply this result, this is greater than delta, where delta is, as we have computed in the proof the previous step. We have actually computed this and showed that such a delta exists. So this is what you obtain. And now you see that T is linear. Therefore, what you have? You have 1 by norm x is greater than delta. Okay, for x not equal to 0. So what is the consequence of that? That is norm of and this is true for see even when x is 0, what happens is when x is 0 you see that the inequality becomes an equality and that is 0 equal to 0. So for every x belonging to right. So if you want you can put this and t0 equal to 0 therefore this is true. So this is the result that we can immediately prove. Now we are further assuming that T is a bijection. It's a bijection of x onto that is what we have proved, which is both 1 to 1 and on. Okay. Therefore, T inverse exists as a map y into x, and in fact this is an onto map. Okay. T of T inverse, in fact what you have is T inverse of T equal to I on where T is from x to y and y to x, that is the identity operator on x. Now it is not difficult to verify that T inverse is given. So the inverse image or inverse map of a linear map from x onto y is also a linear map from y onto x. Moreover, inverse is also a bijection of y x. Okay, so consequently now we will make use of this. let equal to y. Now y belongs to, then x is equal to t inverse of therefore you have from this relation the relation star double stars implies y is greater than or equal to delta of t inverse of, because x is equal to t inverse of y. Okay, that is one upon delta that is a bound for t inverse is given by one delta. Okay. So we have this result norm t greater than or equal to delta and norm of less than or equal. Okay, now this is what we want. Thus, both t and t inverse are bounded linear operators. Linear transformations. T from x to y and t inverse from y to both are bounded. Okay. Consequently, T inverse has the property that open sets in X onto Y onto open sets in X. Both T and T inverse are open. So that's the conclusion that we make, and that's a corollary that we get immediately. So with an additional condition that T is also 1-to-1, we get the existence of T inverse as a bounded linear transformation from y to x, which is also not only T is open, but T inverse is also. And obviously T inverse is continuous. So also T is also continuous. It is given that both T and now T is continuous, but not only that, T inverse is continuous. So T inverse is both a continuous map as well as an open map. Thank you very much. It's a very short lecture, and that concludes our discussion on the open map. Thank you very much.